Have you ever wondered why some things float in water while others sink? It's a fascinating question, and the answer lies in the science of density and buoyancy. These are terms we've all heard in school, but how do they work in everyday life? Why do boats made of heavy metal float while something as small as a stone sinks immediately to the bottom of a lake? Well, the explanation isn't as complicated as you might think once we break it down. Density is basically how much stuff or mass is packed into a certain space, or volume. Think about it like this. If you take a small rock and compare it to a big sponge, the rock feels heavy for its size because it's packed tightly with material, while the sponge is mostly air and feels much lighter. Even though the sponge is bigger, it's less dense. In the case of water, its density is 1 gram per cubic centimeter. So if something has a density less than water, it'll float. If it's denser than water, it'll sink. The wood is less dense than water, which is why it floats. Most woods have a density between 0.6 and 0.8 grams per cubic centimeter, less than the density of water. This explains why not only small pieces of wood float, but also why huge wooden ships stayed afloat back in the day. On the other hand, metals like the ones used in coins are much denser than water. For example, copper, a common metal found in coins, has a density of around 8.96 grams per cubic centimeter, far higher than water. So no matter how small the coin is, it will sink because its density is greater than water's. But let's take a deeper dive into how floating actually works. It's not just about density, there's another force at play called buoyancy. To put it simply, buoyancy is the upward force that water pushes on an object. When you drop something into water, the water pushes back up. If the force of the water pushing up, buoyancy, is stronger than the force pulling the object down, gravity, the object floats. If the gravity is stronger, the object sinks. Here's a fun fact about this. Archimedes, an ancient Greek mathematician, discovered this principle of buoyancy. According to the story, Archimedes was sitting in his bath when he realized that the more of his body that went under the water, the more water was pushed out of the tub. He famously shouted, "Eureka," and ran through the streets naked. What he had realized was that any object submerged in a fluid is pushed up by a force equal to the weight of the fluid displaced by the object. That's why even today it's called Archimedes Principle. A great example of Archimedes' Principle at work is a boat. Think about those enormous cruise ships which are made of metal. By all logic, they should sink like a coin, right? They're made of dense materials like steel. However, ships are designed to displace a large volume of water, meaning that the amount of water they push out of the way is greater than the ship's weight. This creates a strong upward force that keeps the boat floating, even though the material it's made of is very dense. It's the shape of the ship and the hollow space inside it that matters. Speaking of displacement, have you ever tried floating in the ocean versus floating in a swimming pool? You may have noticed it's easier to float in the ocean. That's because saltwater is denser than fresh water. In places like the Dead Sea, where the water is extremely salty, people can float with almost no effort at all. The salt adds to the density of the water, making it easier to displace more water and increasing the buoyant force pushing you up. Temperature also plays a role in whether something floats or sinks. Cold water is denser than warm water. This is why icebergs float. They are made of frozen water, which is less dense than liquid water. The density of ice is around 0.92 grams per cubic centimeter, which is just under the density of liquid water. This is why most of an iceberg is hidden beneath the surface, with only a small part visible above the water. The phrase "tip of the iceberg" comes from this idea, implying that what we see is just a small part of a much larger hidden mass. Now let's think about submarines for a minute. Submarines are essentially giant metal tubes, yet they can float on the surface or sink down deep into the ocean, depending on what the crew needs. How do they do it? They have special tanks called ballast tanks that can be filled with either water or air. When the tanks are full of air, the submarine floats because the overall density of the submarine is less than the water around it. When the crew wants to dive, they fill the tanks with water, making the submarine denser than the water, causing it to sink. By controlling the amount of water in these tanks, submarines can hover at different depths or rise back to the surface. Interestingly, there are also natural occurrences of buoyancy and sinking outside of water. For instance, hot air balloons float in the air, not because they displace water, but because they displace air. Hot air inside the balloon is less dense than the cooler air outside it, so the balloon rises. Once the air inside cools down, the balloon slowly descends. It's the same principle of buoyancy, just in air instead of water. On a smaller scale, surface tension can also make things float, even if they're denser than water. If you've ever seen a tiny insect like a water strider walking on the surface of a pond, that's surface tension at work. The surface of the water acts like a skin that supports the weight of the insect, allowing it to float without breaking through. This concept of floating and sinking even applies to people. Ever notice that some people seem to float easily in water while others struggle to stay on the surface? This comes down to body composition. Fat is less dense than water, while muscle is denser. So someone with more body fat tends to float more easily than someone with a lot of muscle. This is why swimmers sometimes take deep breaths to increase the air in their lungs, which lowers their overall density and helps them float better. In the end, whether something floats or sinks is all about the balance between its weight and the buoyant force of the water or air it's in. Archimedes figured this out thousands of years ago, and today we use that knowledge to build everything from ships to submarines to hot air balloons. So the next time you see an iceberg, or toss a coin into a wishing well, or even just watch a leaf float on a puddle, you'll understand the science that's quietly at work behind the scenes. Floating and sinking aren't just random acts, they're part of a larger dance between density, buoyancy, and the laws of nature.